Good afternoon everyone. Thank you for joining me for this additional video on complex numbers. Today we will be focusing on part 1 of the de Moivre's theorem. I don't know if that's the exact pronunciation of that name, this French mathematician, but in an effort for me not to mispronounce his name, let's just say for video's sake we'll call it DM theorem. It's a French name. With regards to the specific theorem and the complex number topic that we've been talking about, we are going to split this concept of this theorem into two parts. We're going to be talking about the powers of complex numbers in this video, and in the next but the last video on complex numbers we'll talk about roots of complex numbers. Now, as you know, up till now we've talked about imaginary numbers in general. Then we went on to talk about the complex numbers, which had the form basically a plus bi, right? And then we went on to talk further about this being the real number component, this being the imaginary number component. We also talked about modulus. We also talked about the argument of the complex number. We talked about the complex plane. We talked about polar forms, trigonometric forms. Then lastly, we talked about these aspects, z1 times z2, and we also talked about z1 divided by z2, the complex number operations, multiplying them and dividing them. Right? Given the fact that we've talked about all of these different parts, especially with regards to the establishment of these two equation forms, the z1 times z2 and the z1 divided by z2, let's do a quick review example to bring in or refresh the concepts before we jump into this topic of powers of complex numbers. The example that I want to present is going to be nothing out of the ordinary by any means. It's going to be straight and to the point, something that you should be able to handle easily. Let's present that example, then we jump into the topic of powers of complex numbers. Imagine we have two complex numbers, or let's put in this one, we have this one 3 minus I, and then we have a minus 2 plus 2i, and all we want to do, we know this is z1 and this is z2. We want to show you z1, z2, and we want to show you z1 divided by z2. And then I want to show you in a different way how you can get the same exact answers, the formal answers and the informal answers, both are going to be identical. But let's look over here. Let's do the entire process from start to finish. You know the process is going to entail writing this and looking at it in terms of coordinates. You got a 3 comma minus 1. Over here, what do you have? A minus 2 comma 2. We've done all of this in the previous example. Do a complex plane analysis, meaning you're just graphing it out. You have a real number component, imaginary number component, real number, imaginary number. But we've converted into coordinate forms. 3 comma minus 1 would be somewhere down over here. It would be 3 across, minus 1 down. Minus 2 comma 2 would be somewhere over here. Minus 2 across and 2 up. You got to find the modulus. You know the modulus is basically is equal to the square of these two components, and you do the square root. Very much like what you saw in the vectors videos. You're going to do 3 square plus 1 minus 1 square, you'll square root that, you'll get a root 10. Modulus here is a root 10. It's basically just the distance of the connecting line from the origin to the intersection of the points. That's your modulus. The modulus over here, you know, would be a root 8. It could be 2 root 2 or root 8. We'll keep it at that. The next thing we need to do is determine the argument. We've shown you how to do all of this in the previous video. Argument involves the arctan. Remember, the argument involves the tangent function, but you're doing the arctan, and then you're taking the y value and dividing by the x value. What's the y value over here? It's a minus 1, and the x value is a 3. So do a 1 minus divided by 3 on your calculator, inverse tan it, you get a minus 18.43. You get a minus 18.4. But you gotta do this in relation to the quadrant you're in. It's minus 18, but from this 360 degree line, take it down. What's 360 minus 18.4? Because you're a fourth quadrant angle. You're gonna get a 341.6 degrees. Now look over here for this. You have a minus 2 and a 2. You're going to do inverse tangent of the y divided by the x. You'll get a minus 1. You do inverse tan of that, you'll get a minus pi over 4. But you're getting a 45 degree angle in the second quadrant. Well, and you use 180 as your reference angle, and you get 135 degrees. You do 180 minus 45, you get 135, which is what? 3 pi over 4, right? 3 pi over 4. Now you gotta write these in your polar form. The trigonometric form, the polar form are all synonymous. This first item over here, complex number in its trigonometric or polar form would be root 10. We can say z1 is equal to r times the trigonometric aspects of it, root 10 times cosine 341.6 plus I sine 341.6. These are the polar or trigonometric forms. What about our complex number z2, which is all being derived? Remember, these are our initial questions right here. z1 and z2, we're converting these into the polar or the trigonometric forms. z2 is basically a root 8 times cosine of 135 plus I sine 135. Right? Polar forms, trigonometric forms for both complex numbers. Now what we have to do is basically do the actual operation z1 times z2 and z1 divided by z2, and we know the formula for that. When you're doing the multiplying aspect, you're going to add the angles. When you're doing the divide aspect, you're going to minus the angles. So you're going to multiply the r components when you're doing this part, and you're going to divide the r components when you're doing this second or the latter operation. Let's make some room over here and actually do this. Actually, let's make some room right over here on the side. Remember, we're still presenting this initial review, which is a comprehensive review of what we've done prior, and then we'll delve right here into the powers of complex numbers. So z1 times z2 is basically going to be r1 times r2, which is root 10 times root 8, which is a root 80. Then you're going to do cosine of these two angles, added 341.6 plus 135 is a cosine of 476.6. Let's do over here plus I sine, again 476.6. Now what about z1 and divided by z2? You're going to do r1 divided by r2, root 10 divided by root 8. Okay, root 10 divided by root 8. You can just write that as root 10 divided by root 8. And then you're going to do cosine, you're going to minus two angles, 341.6 minus 135. 341.6 minus 135, you're getting a cosine of 206.6 plus I sine 206.6. It's exactly the same values always here and over here, the same values. Now we have to actually formalize and present you the correct answer for each of the operations. So let's come over here. When we do z1 times z2, this is what our answer is. We're going to do this all using the calculator. Everything in quick, efficient strokes. We're looking right over here at this line. Root 80 times cosine 476.6 plus I sine 476.6. The technique over here is do root 80 and square root it and save that value into your memory. Then do individual and you'll hit it with your memory recall. Let's do 476.6 cosine multiplied by my memory recall. I get a minus 4. Okay, I get a minus 4. So the real part, I'm getting a minus 4. Now let's do the second part, the imaginary part. Sine of 476.6, sine it and multiply by my memory recall value, I get it 7.99. Remember, due to decimal placements, we're getting very close answers but not exact, but we can always round up. I'm getting a plus 8i. I'm getting a minus 4 plus 8i. That's my z1 times z2, minus 4 plus 8i. Now let's look over at the z1 divided by z2 again. Let's do the root 10 divided by root 8 and we save that into our memory function. I'm going to save that. Now I'm going to do cosine 206.6, multiply with my saved value, then I'll do this and multiply with that saved value. 206.6 cosine times it with that, I get a minus 0.999. But I can round that up to minus 1, nothing wrong with that. So z1 or z2, I'm getting as my first part, my real part, I'm getting a minus 1. Now let's complete it with the imaginary part. 206.6 sine times that memory recall, which is representing the quotient of these two numbers, I get a minus 0.5, but it's a minus 0.5i. Minus 0.5i. So, here are my operated values. z1 times z2, the two complex numbers multiplying to give you this, and the two complex numbers dividing to give you this. Let's keep these values down over here because I'm going to show you exactly the same way you could have gotten this through a much easier process. By simply just multiplying these two or simply dividing these two, you'll get the exact same result. Then I'll show you why we have to go through such an elaborate process when we could have gotten the exact same values using the much easier process. Okay, now when you look over here at your screen, I've created room over here. You know what we just went through, this elaborate process to get the values for z1 times z2 and the values of z1 divided by z2. The product of the two complex numbers and the quotient of the two complex numbers. And you saw that elaborate process involving the polar forms of each complex number. Now look at this other way of doing it. z1 times z2 is just simply, you can say 3 minus I times minus 2 plus 2i. And we're not we're not doing any conversion here to polar trigonometric forms. We're just taking the two complex numbers and multiplying them out. Look what we get. You're just going to do the FOIL method. Now you just have the simple simplification over here basically. Minus, let's look at this. Minus 2i squared by means of this I squared becomes a plus 2. Minus 6 plus 2 is a minus 4. See, minus 6 plus 2 is a minus 4. And 6i plus 2i is a plus 8i. So the product of the two complex numbers z1 and z2 yielded this, which also matches what we have here using a more elaborate process. Now let's look at the quotient of the two complex numbers, z1 divided by z2. It's not going to be any more hard. It just will have the extra step involving the rationalizing. Look over here, you have to rationalize this complex number, and you rationalize using the complex conjugate. You only look at this middle sign here and you flip it around. Positive becomes minus, minus 2, minus 2i. The same thing on the bottom, same thing on the top. Now you just have the same set of operations, numerator and denominator, and you have to carry them around. But anytime you involve conjugates, you'll eliminate intermediate terms. Remember a squared plus 2ab plus b squared, the 2ab is the intermediate term. You only have to worry about the ends. But here only for the denominator. You'll still have the intermediate term develop here in the numerator because you don't have any kind of a conjugate involved. Let's look at the denominator first. Minus 2 times minus 2 is a 4. 2i times minus 2i is a minus 4i squared. I'm not even doing the other parts because I know they'll cancel out. Let's look at the top. 3 times minus 2 is a minus 6. 3 times minus 2i is a minus 6i. Minus 1 times minus 2 is a positive 2i. Minus 1 times minus 2i is a positive 2i squared. Just simplified. 4 minus minus 4. This I squared negates the minus and makes it a 4 plus 4. On the bottom you'll get an 8 because you get a 4 plus 4. Look at the top, combine the like terms. Let's look at this. 2i squared is really a minus 2i because I squared, as we know, is equal to a minus 1. Well, minus 1 times this 2 becomes a minus 2. Minus 6 that plus that minus 2 becomes a minus 8. And now combine the other like terms. Minus 6i plus 2i is a minus 4i. Remember, you can always take this entire still over here, view it slowly and see what's actually going on. All you gotta do is simplify over here. You'll get a minus 1 minus 1 over 2i, which is the same thing as minus 1 minus 0.5i. We have this answer representing here the product of the complex numbers, and this answer representing the quotient of the complex numbers. Look, exactly the same. So now you might think, if supposedly I'm getting the same answer by simply doing the easier process, then why go to the more elaborate process? The reason for that is when you go through the more elaborate process, you develop something which you do not develop by this technique, and that is those polar forms or the trigonometric forms. See, you develop the polar forms. Remember, we had the polar form over here which was involving the modulus and it was involving the argument. Well, you're not involving any means of modulus or argument in this process, and by developing the polar forms and the trigonometric forms, which are the same, two words for the same item, you can take these complex numbers and do more with them in terms of just multiplying and dividing. You can do more with them. You can do powers of complex numbers. You can do roots of complex numbers. So by going through the more elaborate process and developing those polar and trigonometric forms, you can actually apply these in applications. Whereas in these shortcut techniques, you lose the ability to do all that. So with that review just ending for this video, let's actually delve into the topic of powers of complex numbers. So for this de Moivre's theorem, when we're talking about determining the powers of complex numbers, or we can say the DM theorem, in case I'm mispronouncing that person's name, the mathematician's name, we're basically looking at the trigonometric or the polar forms of complex numbers, and we're trying to determine what would happen to this trigonometric form's value if you were to multiply, if you were to apply some power to it. Like what would be z to the power of n? N could be like 1, 2, 3, whatever. So that's what we're doing here. We're trying to develop a concept over here or technique so we can determine the powers of these complex forms. But if supposedly someone were to ask you what's just z square, assuming that the complex numbers we're using are the same. Look over here, z square. If z is represented by this, what's z square? You know it would be just z times the same z. That's why I'm saying the same numbers are being multiplied, right? We're doing z square meaning the same numbers multiplying by itself. If we're doing z to the n, we're saying that the same complex number, the real imaginary part, is multiplying by itself n number of times. But how would we actually do z times z? Well, For something very small here in terms of the order or the degree, the exponent that's being utilized, it's not very difficult. All you do is just take the same thing and you multiply it by the same thing. For small numbers of exponents, it's actually easy. You see, I'm doing the same thing and I'm multiplying it by the same thing. But you can do that when the exponent number is small. Now, you couldn't really do that if supposedly the question was what's z to the power of 10. Now, in that, you need some sort of technique. But by showing you this easy process over here, we're going to help in developing that technique so you can use the same process for something more complex. But technically, what would you do? You just take this r and you multiply with the same r, you'll get r squared. Then you just do this part over here and you'd multiply by exactly this part over here. Look what you would do. You do the FOIL method, this with that, that with that, and then the inner terms with that other part. You do this with this, and then this with that, then you do this with this, and then you do this with that. And let's do it just for this sake of just showing you the easy process involving an easy exponent. You'll get basically a cosine squared theta. Then here you'll get plus I sine theta cos theta, and you get the exact same thing over here with this inner term, I sine theta cosine theta, and then you'd get plus I square sine square theta. You see this term right here multiplying with that, you develop that I square. And then let's close this off. So right now z square is yielding this, but we got to simplify it all. Cosine square theta, and this right here becomes minus sine square theta. See, I square is equal to minus 1. You remember that from one of the videos. I square is always equal to minus 1. So this thing becomes minus sine square theta. Cosine square theta minus sine square theta. If you think back to the video on trigonometric identities, is equal to cosine 2 theta. Remember, cosine 2 theta was equal to three things. It was equal to cos square theta minus sine square theta. It was also equal to 2 cosine square theta minus 1. And it was also equal to 1 minus 2 sine square theta. But this cosine square theta minus sine square theta gives you cosine 2 theta. But combine these over here. What do you get? You get the doubling effect, right? Two items similar when adding, you're doubling them. 2i sine theta cosine theta. Rearrange it a little bit, this latter term. We still have cosine 2 theta over here. Rearrange it. Bring the I out and bring the 2 with the trigonometric components. And now you can see 2 sine theta cosine theta is a trigonometric identity. Sine 2 theta is equal to 2 sine theta cosine theta. The similar type of identity for cosine, but this one is for the sine. So your final answer is r square cosine 2 theta plus I, let's be neat over here, sine 2 theta. That's my answer for z square. But what's the lesson learned over here? The lesson learned is this: if you start slowly increasing these exponent powers 2, 3, 4, 5, 6, you're gonna end up getting a technique or a formula. The formula will look like this. Any complex number to the power of n will always yield you that r, your modulus to that power of n. And now let's do something about the arguments. It'll always be cosine. You'll have to determine your argument, but there'll be that n value will pop up over here as the coefficient of this argument, plus I sine that n power will show up here as a coefficient of this argument. And this right here will be your DM theorem when it comes to powers of complex numbers. I hope you see that. Remember, I showed you this using a complex number which has this, like this complex number would ideally have started you with something like this: z is equal to x plus iy. You remember that, and you remember how we can convert that into this form, the trigonometric or the polar form. When you're given a question which looks like this, you convert it into the trigonometric or polar form. But I showed you a very easy example, and I opened it out and I showed you what your result is. The square, the exponent is retained on your modulus, and it comes in as coefficients of your arguments within the parentheses. The actual vector or the trigonometric components of these imaginary numbers, that power, whatever it may be, comes in as a coefficient. So you can end up writing the actual theorem for the powers of complex numbers in this form. Your key items are here. The n over here, the n over here, the n over here, and the n over here. So z, a complex number to whatever power, is equal to the modulus of that complex number to that same power. But these inner components, the arguments, are affected in terms of the coefficient by that n value. This right here is the powers of complex numbers portion of this theorem. And we can cement this concept by looking at some practical examples. By practical, I mean examples which will involve the application of this specific powers of complex numbers theorem. Remember in the beginning part of this video, I told you that we're going to split this theorem into two parts. One will deal with the powers of the complex numbers. See these powers of complex numbers, the subject of this video, and then we'll talk about roots. You know, roots in terms of the radical components of complex numbers, but that'll be in the next but last video on complex numbers. And this right here is the theorem, part of the theorem that we have developed so far with regards to the powers of complex numbers. You'll always start with a complex number, as you know, in the format of z is equal to x plus iy. You don't know what your r is, you don't know what your modulus is, you don't know what your modulus is, and you don't know what your argument is. You have to determine, or you have to convert this into the polar and or trigonometric form, which are basically the same. Then from there you'll continue to the finalization of this process. Think about this in terms of coordinates, -1 comma √3, because that helps you visualize this in terms of the coordinate system quadrant that you're in. -1 √3, you know where you'll end up with over here. -1 here, √3 here, and you know we're looking at, we're basically looking at trigonometric ratio numbers 1, √3, and 2, which clues you into a specific angle, which will be I believe 60 degrees. 60 degrees in the second quadrant, which you know is 120 degrees. Anyhow, if you didn't pick up on that, you know it's 1 square plus √3 square, square root of that, you'll get a 2, because you get 1 plus 3 is a 4, square root of that, your r value, your modulus, will yield you a value of 2. And you know the argument can always be determined from the arctan of y over x. √3, let's do square root of 3 divided by 1 minus, and you arctan it, you get a -60. But -60 refers to -60 from 180 degree reference line. What's 180 minus 60 is 120. And you know 120 is basically 2 pi over 3. Remember, we're right now converting the raw complex number into its polar form. We know our value over here is 2 pi over 3. Okay, let's write this in its trigonometric form. The polar form, which is always z is equal to r cosine theta plus I sine theta. And you know what our value over here is 2. And we know cosine is 2 pi over 3, which is 120, plus I sine 120. Now the question was, find this to the power of 12. So we're basically saying, what's z to the power of 12? What's this complex number to the power of 12? Which is the same thing as saying, what's this polar form to the power of 12? All of this to the power of 12. What is this? Meaning z to the power of 12. So that's the process we have to use over here with this theorem. It's not hard. You write r to the power of 12. R here is 2. 2 to the power of 12. Write your cosine value. You're just plugging in things over here. Once you've developed your polar trigonometric form, it's easy. You're just plugging in the n values. N over here is 12. N is always equal to your power. N is 12. Cosine 12 times 2 pi over 3. Remember, inside, with regards to the argument, the n value becomes the coefficient of the argument. But with regards to the modulus, the n value becomes the power of that modulus. Plus I sine 12 times 2 pi over 3. Now, you can calculate your way through this. What's 2 to the power of 12? 2 exponent 12 gives you 4096, 4096. Now let's look over here. 120, which is 2 pi over 3, right hand angle, 120 times the coefficient 12. Cosine this value, I get a 1. In the parentheses, I'm getting a 1 over here. Let's see what happens with the sign. I have a feeling it's going to zero out. 120 times 12, which is my coefficient, my n value, the power. Sine this, I get a 0. So I'm basically getting 4096 plus 0i, and you know what your final answer is, 4096. That's your answer. So the question was, what's -1 plus I √3? What's this complex number to the power of 12? Well, it's 4096. And we did that by using this part 1 of this DM theorem, the powers of complex numbers. We should do several more examples so we can get these concepts clear as we get into the next video, which will be slightly more hard. Remember, determining the roots of these complex numbers will be more difficult. Determining the powers of these complex numbers is much easier. Let's do more examples for this video. Our question is this: what's this complex number? 1 plus I to the power of 5. You know your complex number in reality is really this: z is equal to 1 plus I. You have to determine this to the power of 5. Okay, the complex number. We're going to use this formula after we've converted this into the polar form. Write this out in its coordinates. It's really 1 comma 1. Technically, that's all what it is. You look at it 1 this way, 1 up, 1, 1, and you know your r is a 1 square plus 1 square, root of that is a root 2. You know your modulus is always equal to the tan theta is equal to y or x, or the inverse tan of the y value divided by the x value. 1 divided by 1 is 1, inverse tan of that. Inverse tan 1 is going to give you 45 degrees. 45 degrees is pi over 4, 45 degrees, easy angle. You write this in its polar form or the trigonometric form. Z is equal to root 2 cosine pi over 4 plus I sine pi over 4. Basically, if you think about it, determining the polar form from this raw form or the basic complex number form is really the harder part of this question than the actual determination of the power. We're basically asked to determine what z to the power of 5. Z to the power of 5. You know what you gotta do is apply the n values over here. It's really root 2 to the power of 5. And then cosine 5 times pi over 4 plus I sine 5 times pi over 4. See this right over here is my n theta, cosine n theta plus I sine n theta. All you gotta do, open it up. If you think about root 2 is really the same thing as saying 2 to the power of 1 over 2. But 2 to the power of 1 or 2 is being multiplied by this, to the power of 5, a to the mn. Right? Remember the a to the mn rule for law of exponents is equal to 2 to the power of 5 over 2. Now multiply over here, 45 times 5, pi over 4 times 5, 45 times 5, I'm getting a 225. When you cosine it, you get a minus 1 over root 2, which is a minus 0.707. This is really a minus 1 over root 2. These are third quadrant angles, so you know this is going to be minus I over root 2, which will be minus 1 over root 2 times I, which is minus I over root 2. You got to open up the parentheses. When you open up the parentheses, you're going to individually multiply over here. Think about it all in terms of this. Let me simplify it by writing it in a different way. Minus, look what I'm doing over here, 2 to the power of minus 1 over 2. Minus, this will minus, well let's not skip a step over here. I'll be doing a minus here, minus 2 to the power, 2I to the power of minus 1 over 2. Why did I do this minus 1 over 2? Because minus 1 over 2 is the same thing as 2 to the power of minus 1 over 2 is the same thing as 1 over root 2. If you open up all of this, over here you get a minus 2 to the power of, remember when you're multiplying exponents with the same bases, you add, you'll get a 2 to the power of 4 over 2, which is a minus 2 squared, you'll get a minus 4. You can work this out on your side alone and confirm that my answer is indeed right. I see I've made just a little mistake. I shouldn't even have put a minus over here, because just because I'm bringing it up, I don't add a minus. The minus comes here in the exponent. If you open this up over here with this, you'll get a minus 4i. And your answer should be minus 4 minus 4i. So therefore z to the power of 5, meaning this to the power of 5 is equal to minus 4 minus 4i. You'll be able to confirm this again. This minus I over root 2, let's just do this for clarification's sake. Minus I over root 2, which I was incorrectly putting another minus over here, was the same thing as saying minus I times 2 to the power of minus 1 over 2, because anything to the power of minus is a reciprocal. You simplify this, you get minus I times, well, you open up the parentheses, minus 1 over 2. See, minus I 2 to the power of 1 over 2, but this minus is right here outside the parentheses. We should not have added a second minus over here, because we would have negated it and created a positive here. But this here is our right answer. Okay, it's the correct answer. Minus 4 minus 4i. That's right. This question is done. Let's look at some more examples. In this case over here, our complex number z is equal to minus 1 plus I. Remember again the real number component and the imaginary component. We basically have this entire complex number to the power of 10, and we have to determine what z to the power of 10 is equal to using that, but only after we've converted this basic form into its polar form. You know, basically, again, you're going to convert this into coordinates. It's minus 1 comma 1. You can always graph it to help visualize which quadrant you're in. Minus 1 comma 1 puts me right over here in quadrant number 2. We're minus 1 to the left, 1 up to the top. And you know, just by looking at that, your modulus is equal to root 2. Minus 1 square plus 1 square root of that is root 2. And by looking at theta, you know, it's arctan of 1 divided by minus 1, which will give you a minus pi over 4. Minus pi over 4, because tan of a minus 1 is a minus pi over 4. Remember, tangent is not an even function. It's an odd function. So when you're doing a tan of a minus answer, you get a minus answer. Minus pi over 4 is with reference to this 180 degrees. 180 degrees. You're going to go 45 degrees that way. And you're going to end up getting a value called 135, which is really 3 pi over 4. Easy. You can look at that review of fundamentals of trigonometry video to see some of these nuances which I'm talking about here. Your polar form is this. Z is equal to R, which is root 2 times cosine. Let's keep it 135. You could have written cosine 3 pi over 4 plus I sine 135. Nothing wrong with using angles or nothing wrong with using radians. Now you have to determine what z to the power of 10 is. So then that, of course, is root 2 to the power of 10. Remember this formula here? R to the power of n, the modulus to the power of n. In terms of the arguments, you know the angle here represents the argument. You're doing the coefficient. You're not doing 135 to the power of 10, you're doing 135 times 10. It's n theta. Plus I sine n theta. N over here is 10. What are your question is asking you in terms of your power? This right over here, power is your n value. Now everything over here you can do with the calculator. Everything can be done with the calculator. What's root 2 to the power of 10? You'll get 2 to the 1 over 2 times 10, you get 2 to the power of 5, which will be 32. If you didn't see that, it's alright. You can do square root of 2 and you can do exponent 10, you get 32. Now do these individually. 10 times 135 cosine, I'm getting a 0. This over here zeroes out in terms of cosine, so it must have been like one of those 90-degree multiple angles, something on the y-axis which zeroes out in terms of the cosine. What's sine 10 times 135? 10 times 135, sine it, I get a minus 1. So it's basically a coterminal angle of a 270, which is why cosine was coming out 0, but sine is coming out as a minus 1. Remember, a value on this axis would be 0 comma minus 1. The cosine value of something over here would be 0 and sine would be a minus 1. You can do 1350, which is 135 times 10, 1350, and you divide it by 270 and you get a whole number answer 5, which means it was an angle or a coterminal angle of 270. You can land on this angle 1 time, 2 times, 3 times, 4 times, 5 times, and you'll end up with 1350 right on top of that. Coincident points. But what's our final answer? It's minus 32i. Z to the power of 10 or minus 1 plus I to the power of 10 gives you a minus 32i answer. That's the answer of this complex number to the power of 10. One more question and then we'll call it for this video. So here's our last question. We're going to determine the power of this complex number. But before we actually dive into this question, remember we're looking at questions which look like this. We're given a complex number which looks something like this: x plus yi, a real number and an imaginary part. We're determining the r value, the modulus, and we're determining the complex numbers argument to create a polar form. The polar form will actually look something like this, as you know: r cosine theta plus I sine theta. Unless these parts are not already given, you always have to convert this into this form. Sometimes you can have a question which is already given in this form, you just have to apply this and you're done. But then of course we're taking this to the next step to determine actually z to the power of n by means of this formula. So on all of these questions you're actually going through this extra step, call it practice, to determine the trigonometric form, to determine the power of that complex number. Sometimes tricks can come in like this, as you see over here, and I'll tell you what I'm talking about when we actually start it momentarily. The question is seemingly easy, and it is actually, unless you don't make a specific mistake. The question is this: 2 times parentheses root 3 plus I to the power of 7. Your complex number portion is really only this over here. So really, if you say my complex number is root 3 plus I, you're good. If you look at this carefully, the 7 power is affecting only this underlined part. It's not even 2, it's not even hitting 2. 2 is outside it. So don't make the mistake of thinking of this question as opening it up. You don't want to make this mistake of this 2 root 3 plus 2i to the power of 7, because that'll be wrong. If you do that, it'll be wrong, because 2 is outside the parentheses and it's not impacted by the power. The way you want to handle this question is how I will show it to you. And this is what you're going to do. You're going to take this 2 and you're going to push it aside. Just push it aside and look at only the parenthesized aspect, which is affected by the power. My question is this now. Z, complex number, is equal to root 3 plus I. My real number, my imaginary portion. Convert this into the coordinates. Root 3 comma 1. Graph it on a complex plane. Root 3 on the x-axis and 1 on the y-axis. Right? Root 3, 1. Again, trigonometric ratio is 1 root 3, and you know 2. Or do root 3 square plus 1 square, root that, and you'll get a 2. Angle, my argument, is always equal to arctan of 1 over 3. Arctan of 1, or let's not even say 1 over root 3. Let's say y over x. The y component divided by the x component. If you do this computation, or you realize this is one of those trigonometric ratio triangles, it's a 30, 60, 90. You know your theta is going to be 30 degrees or pi over 6. Because only a 30 degree would oppose a smaller side, and the 60 degree would oppose the root 3. And you know this right here is a right triangle. Anyhow, our angle is 30 degrees or pi over 6. Write this in the trigonometric polar form, which would be that z is equal to 2 times cosine pi over 6 plus I sine pi over 6. We have to determine z to the power of 7. And remember, I haven't forgotten about this too. I just pushed it aside. Put it in the form that's 2 to the power of 7 times cosine n theta, 7 times pi over 6, plus I sine 7 pi over 6. Remember, 7 times pi over 6 is nothing more than just saying 7 pi over 6, which is really 210. Pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. These are my 30 degree angles. 7 pi over 6 is 210. Let's bring the calculator. Let's not get too fancy. 2 to the power of 7 is 128. Cosine 7 pi over 6, we're looking at a 210 degree. 210 degrees. Cosine 7 pi over 6 would be right here, this reference angle of a minus 30. You'd get this answer. You'd have a root 3 this way, and you'd have a minus 1 here, and you'd have a 2. So cosine 7 pi over 6 would be minus root 3 over 2. If you don't accept this method, use a calculator and do decimal answers. Decimal values, and you get the same answer. Minus sine 7 pi over 6, 7 sine of 210 would be minus 1 over 2. Minus I over 2. 1 over 2 I is same as minus I over 2. Do everything over here. 128 would get divided by the 2. You get 128 divided by 2. You'll get minus 64 root 3. Minus 64 root 3. And you'll get a minus 64i. Let's not add a double minus, because we still have the same minus in between this minus I over 2. So you have minus 64 root 3 and minus 64i. But we have to bring back this 2. Hit everything with this 2 to give you your final answer. Let's put it right over here. My final answer, z to the power of 7, is this. It'll be minus 128 root 3 minus 128i. I just remultiplied everything by 2. Remultiplied it. And this right here is our final answer. Hopefully not too messy handwriting wise, but we got it. That's the final answer. Minus 128 root 3 minus 128i. So not very difficult. These are the procedures involved in determining the powers of complex numbers. Remember, you're starting with the raw number, converting to the polar form, and then utilizing this formula of the DM theorem to determine the power of such complex number. I hope you enjoyed this video. It shouldn't be too hard of a material. Next week when we look at the roots of complex numbers, you'll find that to be slightly more challenging, but again, we'll have a specific formula in place for you to utilize, and it won't be too hard. Please like, subscribe, and share, and enjoy this video. Thank you. Have a nice day. Bye.